This is R13, R13, R12. Okay, so initial potential energy is the potential energy this pair, and that pair. All right, I'm going to, you can see that I've run out of room, so I'm going to and then in the final configuration, it'll be this potential energy plus this potential energy plus this potential energy. And what I'll do is I will write this in the initial. So what the subscript tells you is that's the initial distance, and we'll do the same thing for final. Do you guys understand the notation? Okay. And this will be the final configuration. Plus 1/2 mv squared, which is m3v squared. Okay, this term is the same, so that'll cancel. Because this distance is not changing. These guys are fixed. Okay. Only these distances are changing. But this distance is equal to that distance. Okay. See, this distance is equal to that distance, and that distance is equal to that distance. Okay. So let me calculate R13 initial, which is, this is 3 centimeters. This is 3 centimeters. Okay. So R initial is 3 square plus 2 square, square root of that, 9 square root of 13. Our final is 3 square plus 4 square, 16, 9, 25, 5. So this distance is square root of 13, this distance is 5 units. Charges Q1 and Q2 are the same, so it will be K, Q, Q3. R initial is equal to, this is the same, so equal to 2KQ Q3 R final plus 1/2 mv squared. Okay. The energy of the third charge. Okay. So it's just messy. So 1/2 mv squared equal to 2K Q3 1 over R initial minus 1 over R final. Okay. So V equal to 4K Q, that's Q3. to the power half. All right, so let's put everything in SI units. For K is the Coulomb's constant, and I'm not going to write the units. It just will get messy. Q is 2 microcoulombs, and Q3 is 4 microcoulombs. And the mass is mass of Q3 is 10 milligrams. Milli is 10 to the minus 3, and a gram is 10 to the minus 3 kgs. So 10 times 10 to the minus 6 kgs. And the distances are, our initial is root 13 centimeters into 10 minus 2 meters, and 1.5 into 10 minus 2. What is it that we are calculating? Speed. And so that'll come out in meters per second. Everything is in SI units, okay? All right, let's take care of powers of 10. That's 10 to the 12. That gives us, so 10 minus 3. Then that becomes 10 plus 3. And 10 plus 5. Okay. It was 10 plus 5, then divided by 10. So that's 10 to the 4. Meters per second. 4 into 9 into 2 into 4 into 1 over root 13 minus 1 over 5. Okay, hopefully I've done everything right. Ten to the power of 3 is kilometers, so 22 kilometers per second. 223 kilometers per second. So it'll go from here to Jupiter in 1 second. Yep.
What happened to the square root?
What square root?
V had initially been squared, so you took the square root of everything.
All right, so I didn't do that. All right, so it'll be going a little slower then. Okay, so it's going at 472 meters per second. Half a kilometers per second. So from here to Krispy Kreme donuts. All right, so here's an interesting problem. Okay, when your heart goes into fibrillation, what has happened is it's gone into chaotic beating. And so they'll use a capacitor, energy stored in a capacitor, and pass a large current through your heart. It'll stop it, and then it goes back to regular beating. Okay, so that's what a defibrillator is. And it discharges 400 joules of energy. Okay, so here's an interesting number. In the next chapter, you'll see, you guys have taken flash camera pictures, right? The flash camera pictures, that capacitor discharges about 20 joules through that thing. So to restart your heart, you're discharging 20 times that energy. So what are you doing again? Your heart is chaotically beating for whatever reason, and you're stopping it and restarting, rebooting your heart. I wonder how they discovered it the first time. Hmm? What's that?
Who that first patient was. Who was trying out first.
That's interesting. Oh, that is flashing. Okay. Anyway, so what is the average power output of the heart defibrillator? Okay, so here's the deal with the capacitors. So we'll learn about capacitors next. See, a capacitor can discharge its energy extremely fast. If you stored this much energy in a battery, it would take hours to discharge that. And in a capacitor, you can discharge it in milliseconds. Okay? So power is energy over time. 10 milliseconds. And joules over seconds is watts. Okay, so that is 40,000 watts. So the energy flowing through your heart is 40,000 joules per second. That's a large power. That is, you can run 40 homes with that power. So here's the question. Considering the high power output, why doesn't the defibrillator produce serious burns? All right, so to produce burns, what is relevant is how much total energy was deposited, not at the rate at which the energy was deposited. So this is what causes burns. And I guess your heart is about 100, 200, 250 grams. Somebody, how much is a human heart? Hmm? What? How much does a human heart weigh? Okay, so 300 grams. Okay, so, and let's say you're passing that energy around. So let's say we're passing the energy through 1 kg of your body. Okay? Heat is mc delta T. Okay? And we'll assume that our body is essentially water. I mean, for good approximation, that's good. And so the temperature rise is Q over mc, 400 joules over 1 kg times 4,186 joules per kg per degree Celsius. So that would be the temperature rise about 0.1 degrees. So when they defibrillate your heart, your temperature of your chest will rise by about 0.2 degree Fahrenheit. Okay? You won't even get a fever. Do you guys know how X-rays are produced? All right, so what you do is you take an electron, speed it up, and hit it against a wall. And when the electron stops, all the energy goes into an X-ray photon. Okay, so that's how you. Yeah. And so if this electron were traveling in air, what would happen? Huh?
It would hit or get interfered.
It would bounce off air molecule and lose all its energy, lose its energy. So you have to do this in an evacuated tube. Okay. So an evacuated tube uses an accelerating voltage of 40 kilovolts. So 40,000 volts. So this electron that was at rest, when just before it hits the wall, it has, remember, an electron falling through 1 volt gains 1 electron volt of energy. So falling through 40 volts will gain 40,000 electron volts of energy. Okay? And produces X-rays. Non-relativistically, what would be the maximum speed of these electrons? Okay, so the potential energy, change in potential energy gets converted to kinetic energy. So this is the non-relativistic formula. So as long as the electron is traveling at a tenth the speed of light or less, this formula is good. If you start traveling faster, then this is the correct formula for the energy. Okay. Okay. So essentially the electron is getting heavier by this factor. And what that factor is 1 over c is the speed of light. Okay, so that's how you would calculate the energy of the electron if it was going fast compared to the speed of light. But this is very messy, and unless somebody's buying you a good meal, you don't want to use that formula. Yeah. So this energy is E times delta V. This is 40,000 electron volts. Okay, well, this V is speed. Okay. So the speed is 2e voltage divided by the mass of the electron, square root of that. So the speed of the electron is 2 times 40,000 electron volts. That's that's E, and that's 40,000 volts. Okay, so 40,000 electron volts. And 1.6 times 10 to the minus 19 joules is the conversion to electron volts. 1 electron volts is 1.6 times 10 to the minus 19 joules. And the mass of the electron is 9.11 times 10 to the minus 31 kgs. Okay, so those are constants that you can look up. So that'll be the speed of the electron in meters per second. Okay, so that's 10 to the 4, and that makes this 10 to the minus 15. That becomes 10 to the plus 16. Square root of that is 10 to the power 8. meters per second. 2 into 4 into 1.6 divided by 9.11. What is the speed of light?
3 million meters per second, roughly?
No, 3 times 10 to the power 8, okay? Meters per second. So see, this is coming out in the right order, and this had better be less than 3. Otherwise, Einstein will get upset, okay? So V is 1.18 into 10 to the power 8 meters per second. Okay, the speed of light is 3 into 10 to the power 8 meters per second. Okay, so this is about 1.2. This is about 40% the speed of light. Okay, so really we shouldn't have used this formula. What you really needed to use was, okay, so the total energy is given by, so the kinetic energy of the electron is given by 1/1/2 gamma mv square minus mc square. This is the rest energy, so this would be the kinetic energy. And this is so messy that so this would equal 40,000 electron volts, and you would have to calculate the speed of the electron that way. And that's just too messy. Yep. Okay, so we'll learn about capacitors next chapter. Okay, let me show you. We've seen this app before. All right, so this is what is called a parallel plate capacitor for obvious reasons. So when you connect a battery, again, so let's say when you connect a battery to this capacitor, what happened was electrons flowed from here, these electrons repelled those electrons and came over there. What happened was energy was transferred from here to there. Okay, and the higher the voltage you charge the capacitor to, the more energy you're storing. Okay, so this was a slow energy release device. You transferred it to a fast energy release device. The reason you transferred energy to the capacitor was because this guy can release energy very fast. Okay, and I mean, there are applications, so if you want to use fusion reactors, you want to store as much energy as possible in this capacitor. What is the limitation? Why can't you store an infinite amount of energy in the capacitor? Okay, so there, when you store energy, it's creating electric fields. And if the electric fields gets greater than 3 million volt per meter, what happens?
I think
that air will become conducting, and all that energy stored will go down the drain. So that's the limitation, okay? All right, so there's a maximum amount of energy you can store, okay? So you want that electric field to be less than that critical electric field, and that's what this problem is about. So find the maximum potential difference between two parallel conducting plates separated by 0.5 centimeters of air, given the maximum sustainable electric field in air is that, okay? Above that, air will become conducting, okay? So there's the electric field. The potential difference between the plates is given by the electric fields times that. So V max is E max times D. So the maximum potential differences that you can have is 3 times 10 to the 6 volts per meter. And the distance between the plates is 0.5 centimeters, 0.5 into 10 minus 2 meters. So this is equal to 1.5 into 10 to the power 4 volts. So 15,000 volts is the maximum you can charge that capacitor to. Okay? You will learn next chapter the energy stored in a capacitor is 1/2, C is the capacitance, and V is the voltage. Okay, so the higher the voltage you can charge a capacitor to, the more energy you can store. Okay, can you think of any way to increase the voltage you can charge it to? What you can do is you can put a piece of plastic. So in a plastic, what limited the fact you couldn't charge it more? You didn't want lightning to happen in air. So is there a limit in plastic? Piece of plastic? You can create lightning in plastic. So there's a limit there too. This thing is called a dielectric, okay? So we'll talk about this